Welcome. We often think of our systems as seamless operators, but beneath that calm surface is a constant, high-speed conversation between hardware and software. The most critical dialect in that conversation is the interrupt request, or IRQ. Understanding its journey is not just an academic exercise. For system administrators and engineers, it's the key to unlocking the root cause of elusive performance bottlenecks, system hangs, and driver conflicts. In the next few minutes, we're going to bypass the user interface and dive deep into the kernel, tracing the precise, microscopic lifecycle of a single interrupt, from an electrical signal on a pin to the final execution of its handler. Let's begin. Every interrupt begins as a physical event. Imagine a network packet arriving at your network interface card. The NIC needs the CPU's attention immediately. It does this by asserting a voltage on a specific pin, its physical IRQ line. This signal doesn't go directly to the CPU. In modern systems, it travels to a crucial traffic cop, the I/O APIC, or Advanced Programmable Interrupt Controller. The I/O APIC receives this physical signal and translates it. It maps the physical pin to a system-wide identifier called a Global System Interrupt, or GSI. It then routes this GSI, often over the system bus, to the local APIC of a specific CPU core. The local APIC is the final gatekeeper. It receives the message and prepares to interrupt its core with a specific interrupt vector, a number from 0 to 255 that uniquely identifies the source of the interrupt. This intricate handoff ensures that interrupts are prioritized, managed, and delivered to the right core without chaos. The CPU core has received the vector. Its current task, whether it's running your web browser or a background service, is instantly suspended. The CPU performs a critical automatic operation, a context switch. It saves its current state, the contents of its registers, the instruction pointer, the stack pointer, onto a special protected area of memory called the kernel stack. This is like putting a perfect bookmark in a book, so it can return later without losing its place. With the context saved, the CPU uses the interrupt vector number it received from the APIC as a direct index into a fundamental OS structure, the Interrupt Descriptor Table, or IDT. Think of the IDT as the kernel's emergency contact list. Each entry in this table, pointed to by the vector, contains the memory address of the specific function designed to handle that exact interrupt. This is the Interrupt Service Routine, or ISR. The IDT provides the direct, non-negotiable address, and the CPU immediately jumps to that location and begins executing the driver's code. We've reached the Interrupt Service Routine. The ISR is now running, but it's running at a very high privilege level known as an Interrupt Request Level, or IRQL. At this high IRQL, most other interrupts of equal or lower priority are masked or ignored by the CPU. This is why the cardinal rule of ISR design is to be fast. Its only job is to do the absolute minimum work necessary, like telling the network card, "I've got the packet, you can send the next one," and capture any critical state. The heavy lifting is offloaded. Before exiting, the ISR schedules a deferred procedure call, or DPC. The DPC is the second phase of our handler. It runs at a lower IRQL, specifically dispatch level. At this level, other hardware interrupts can now be processed, making the entire system more responsive. The DPC will do the slower work, like copying the packet data into memory buffers for the operating system's network stack to use. This two-phase ISR DPC model is a masterful compromise, ensuring urgent hardware needs are met instantly while preventing a single chatty device from monopolizing the CPU. So, let's trace our journey one last time. A physical signal from the hardware, marshaled by the APIC, which triggers a context switch on the CPU. The CPU uses the IDT to find the right ISR, which does its critical short-term work and then queues a DPC for the follow-through. This isn't just theory. When you open Performance Monitor and see high percent DPC time, you're not looking at a generic metric. You are looking at the direct consequence of this entire flow. You now know that a driver's Phase 2 handlers are consuming too much CPU time, allowing you to pinpoint the exact driver or device causing system-wide latency. Understanding this anatomy transforms you from a system user into a system diagnostician, equipped to solve the deepest and most challenging performance problems.